where were we? Esters. Okay. So, let's do some practicing, all right? Now, let's just work the first part. What you want to do is you want to see what are the functional groups here, right? So, when you see this, what do you see?
Ester. Or no, like anhydride.
Anhydride.
Oh,
But
yeah.
you know, like ester, anhydride, like all these things are tough, right? So you work through this however you want, but for me, what I would do is I say, what's the functional group? Because that's going to help with the parent name, right? And then I can tack on other stuff later. This is your ester here, though, right? Here, amide, right? Here, anhydride, right? It's a little bit funky because it's in a ring, but it's an anhydride. Here,
Carbox.
yeah, that was an H,
Oh, okay,
carboxylic
yeah,
acid.
yeah.
Yes, an ester. Here,
It's an ester, or no?
yeah, it's a diester, right?
Oh,
Two of them here.
Yeah.
Amide with a ring. So you guys remember when we have a carboxylic acid coming off of a ring, we could call it the cyclobutyl carboxylate or carboxylic acid. So here, this will be in that similar form, okay? And then what's this right here?
Ester, yeah.
Okay. So let's give this a stab and see what we can come up with, all right? We've got that first one. Let's go over that first one together. If it's an anhydride, it's just anhydride, right?
Mm-hmm.
What do we have on either side, though? Or, in other words, like 1, 2, 3, right?
Mm-hmm.
1, 2, 3. It's symmetrical, right? 3 would be
Propyl.
propionic anhydride, or propanoic anhydride, if you want to use the more updated term. Now, this other one here, let's break B down. We have 2 benzene rings, but those are really substituents, right?
Mm-hmm.
Because this is an amide, right, coming off of here.
Mm-hmm.
And there's 1, 2, 3. So N diphenyl. 2 phenyl groups coming off of it, and then it's propionamide, right? Or propanamide. I would accept propanamide because it's too hard for me to pronounce. Propionamide,
Yeah.
right? Propanamide. But you see how you see where that's coming from? You really got to break it up and say, okay, like this right here is the functional group is going to be my parent.
Okay.
What about this one? Well, we have methyls coming off of there, right? And then 1, 2, 3, 4. If we go back in time to last Thursday, what was our system here, right? For 4. 1, 2, 3, 4. Succinic acid. What we've done is we've taken that succinic acid and we've turned it into 2 esters, right?
Mm-hmm.
So this could be a dimethyl, right? Because there are 2 methyl groups. 2 methyl groups here. Methyl, methyl, dimethyl.
Succinate?
if it's an ester, it's 8. Dimethyl succinate. All right, now this next one's challenging, right? But what do we have? We have an amide, right? What's coming off that amide? Not 2 hydrogens in this case. We have a methyl and an ethyl, right? So this could be N-ethyl, N-methyl, and then now what? Now we have a cyclobutane. Cyclobutane. And then when we have a functional group coming off of a cyclic ring, it's carbox something or other, right? So when this was the carboxylic acid, we call it carboxylic acid, right? In this case, we can call it carboxamide.
If you have like 2 ends or like 2, like how could you differentiate, like if there was like a ethyl on that one, or I don't know, like
Yeah,
if
so-
an ethyl on one and then an ethyl on the other instead of just like repeating.
That's where we had the N prime.
Okay.
Okay, so if we had more than one N, we could designate one nitrogen as N prime, and then the other one is just regular N.
Does it really matter? Like
Which one?
Yeah, is prime or
Not to me. I think you could alphabetize it, right? So N could get the E for ethyl, and then the N prime could get the M for methyl. If you have 3, then it's double prime, right? So that's when those long numbers, you start seeing commas in there at the top, and it gets kind of wonky looking. Okay. What's this?
Propyl nitrile.
It's a nitrile, yes. This is so it's not written as this, but that's shorthand, right? So yeah. So 1, 2, 3. Propanonitrile, or 1, 2, 3. Oh no, sorry, there are 4, right? 1, 2, 3. This carbon here. So we do count the carbon that's part of the nitrile. So this would be butanonitrile or butyronitrile, right? We could write it. So butyrate, butyronitrile, or butanonitrile. And so now, what do we say F was?
Ester.
It's an ester. So, ester's going to have 2, and it has 2 potential groups here, right? For the parent, you want to pick, what's coming off of here, right? So we have a 1, 2, 3, so that's a prop. And then we have a 1, 2, 3, 4, right? So esters are 8, right? So that could be a butyrate or a butanate. And propyl butyrate or butanoate. Now this next one, I actually don't remember what the next one. How do we do that? Because there's a ring in there, cyclo.
Yeah.
It's an anhydride, right? One, two, three, four. There are 4 carbons in there. So let's see what that would be. Right? Yep. Okay. Succinic anhydride. So they don't put the cyclic in there. Okay. So you could also, so we could also call that, was it 1, 2, 3? We could call that butandioic anhydride as well. Some diacids here. So butane dioic, this could be, or pentane dioic, this would be 1, 2, 3, 4, this would be butane dioic anhydride, or it could be succinic anhydride. And I guess you don't have to do the cyclic because in order for this to go away, in order for it to be an anhydride, these have to come together.
Oh, yeah, okay.
Right? Or actually, so this would come, yeah, this would be down there. That's a tricky one. Okay. So what's H? H is an ester, right? So 8. We have a methyl group on one side, right? A benzene on the other side. So we could call that methyl benzoate, not phenyl methylate or methylate, right? Methyl benzoate, and then this last one, what is that? That's another ester. So 8. This we could call phenyl acetate. So, right, whatever's coming off that oxygen, here it was methyl, and then this is the parent, right? Here, phenyl, and this is the parent.
Oh,
so
I see.
you gotta see what's you gotta see what's coming off of that carbonyl
Okay.
as your parent.
Yeah.
All right. Functional groups. Let's skip over this part, unless you want to. You want to work on? Actually, we haven't done any drawing. Let's do a couple of these. Dimethyl oxalate. So, oxalate. Go back. Oxalic acid, right? So 2 carbons. Eight means it's going to be an ether. So So, right, we want to have 2 carbons. And then that.
Okay.
Phenyl cyclopentane carboxylate. Ooh. So that means cyclopentane carboxylate. That means this, the phenyl group's coming off of the O of the ester, right? And the cyclopentane is coming off the carbonyl. So 1, 2, 3, 4, 5. Come off the carbonyl. O. And then something like that. N-methylpropionamide, okay? So N-methyl, right? So we got an N here, and there's going to be a methyl coming off of there and a hydrogen, and then what's next? Our carbonyl, and it's
4 or 3.
1, 2, 3. And then, going back to the first one, our halogen, propionyl chloride. So 1, 2, 3.
Okay.
And chlorine. I kind of did that fast. Did we get all of this?
It's a little easier going that direction.
I always like drawing the structures
Yeah.
more than naming because I can kind of dictate where things go. So that's definitely my preferred order as well. But if you know something forward and backward, then you have it mastered. Okay. So I just want to wrap up here a little bit talking about reactivity of these derivatives. And so there is an inverse relationship between the basicity of these leaving groups and the reactivity of the derivatives. All right? So you'll notice chlorine, yes, that's a weak base, right? An amine group or a nitrogenous group is going to be a strong base. We know that
So reduces.
from previous things, right? So this is the order: strong base, and then a hydroxyl, and then an ether, and then an ester, and then chlorine, right? And then there are some things in between here. So right here we got our amide here, and then carboxylic acid here, and then they don't have the ether in here, but here's the, so the ether would be right here in terms of reactivity. Ester. They also don't have an anhydride in here because I guess these things just aren't, well, they're both coming from the same source, but you can see, right, that the weaker the base, the more reactive it is. The more reactive it is means that if the conditions are at equilibrium, it's not going to favor this side because it's so reactive. It's gonna go. Okay, it's going to react. So at equilibrium, you're going to tend to favor these less reactive substituents. Now, if we use Le Chatelier's principles, right, we tweaked things, we could drive it one way or the other, but at equilibrium, weak bases that are more reactive are going to essentially become the reactants, right, and you're going to get the product. And the product favored is going to be stuff on this side of it. And so we can rank it, we can predict, we can say, okay, if I have a carboxylic acid and I want to make an amide derivative at equilibrium, which side of the arrow is going to be favored? It's going to be this one, right? If I'm using this and I'm going to an ester at equilibrium, what's going to be favored? It's going to be this one, and so on. And so this is what's happening here, right? We have our nucleophilic attack. It comes in. We get rid of our double bond here. And the leaving group leaves. And we have our derivative. And again, this is just another way of saying it, right? Under standard conditions, equilibrium will favor the functional group with the strongest group still attached to the carbonyl. Or in other words, the stronger base, the least reactive substituent. So we'll wrap up let's see, perfect timing. Last 10 minutes, let's work on this. So we have an acyl chloride here, and we're wanting to put this on, right? So this is where it's going to attack. This is the nucleophile, so it's going to dissociate from that sodium, and it's going to put on here, right? And if we go back to that reaction, what's going to happen to the pi bond? It's going to go up there, right? We're going to have this intermediate. So this goes up here, and we end up with this is going to be O. Okay, something like that. All right. Then this is going to come down here. Leaving group is going to leave. We end up with yeah, does that look right?
Yeah, that's what I saw.
Cool. And then what else do we have? We have salt in there, right? Chlorine goes with the sodium. So, what's favored though? We should know this because this is the weakest base, right? So it's going to always be the most reactive, and so this is going to be favored at equilibrium. Too many dots, not enough eyes. All right. So what about that next one? That next one, we're going to create, let's do blue. Create another ester. And now we have the difference between an ester and a carboxylic acid, right? So if we go back, carboxylic acid, ester. What's favored? Carboxylic acid, right? This is actually, so, right? This will be favored at equilibrium. Turns out that this is how soap works a lot. All right, we have an esterification, and it breaks down into an alcohol. Right?
So how do you drive that if it's not favored by equilibrium to go towards the ester?
So things that affect equilibrium change, the easiest way would be to increase the concentration.
Oh, okay.
Right? So if you change the concentration of one thing, it will shift equilibrium to produce more of the product, so that it then, we have. Okay.
Yeah. Okay.
Right? That's the most direct way. You can also add heat, and you can also add pressure, right?
Yeah.
But the easiest way to drive this to an ester would be to increase the concentration.
Okay.
And then this last one, we have another chloride, right? Acyl chloride, and we're putting it with ammonia. So we're gonna make it amine, right? We're gonna end up taking off this. We'll have an intermediate, right? Similar to this, where the chlorine is still on there. The nitrogen. So let's see here. Let's. NH3. This is going to go here, this is going to go here. We're going to kick off one of these hydrogens, right? And then we end up with NH2, HCl, right? Hydrogen comes off here, chlorine comes off here, and now we have hydrochloric acid. And look, we have both ends of the extreme, right? We have an amine, which is the strongest base, right?
Yeah.
Least reactive, and a chlorine, weakest base, most reactive. So this
Favorite.
will be favored at equilibrium. All right. So, today in lab, we're going to do our Grignard synthesis. Fingers crossed. Thursday, we'll go over some of those take-home problems. So, what I suggest between now and then, if you want to take another look at that, highlight some of the problems in particular that were sticky or just out of left field, and then we'll focus on those on Thursday. And then if there's some time, we can get into reactions of carboxylic acids. If not, then we'll move ahead, I think, and just go into the next chapter of amides.